Welcome to the Deep Dive series, AI Coprocessors. Today, we are diving into something huge, a real tectonic shift in how AI hardware is being built. You see, artificial intelligence is evolving at a pace that is just completely outstripping the silicon it runs on. And this has created a massive, high-stakes challenge for every chip designer on the planet. The whole problem boils down to a fundamental clash of speeds. On one hand, you have AI software and models that change literally in a matter of months. On the other, you have the process of designing, verifying, and fabbing a complex chip, that's a multi-year marathon. So how in the world do you build hardware today for a future you can't even predict? Well, the answer, as we're about to find out, isn't just about a faster chip. It's about a whole new, much smarter, and way more flexible philosophy of design.
So let's kick things off with the why, because to really get why this solution is so elegant, you first have to appreciate the sheer mind-boggling scale of the problem. We are living through a genuine explosion in the demand for AI computation. And this isn't just a little bump, it's a surge so intense that it's forcing a complete teardown and rethink of hardware architecture right down to the foundations.
And when I say the scale is staggering, I mean it. Just a couple of years ago, if you were designing a top-tier AI chip, you might have been aiming for performance in the double digits of TOPS. And TOPS, of course, stands for trillion operations per second. So we're talking about, say, 50 or 60 trillion math calculations every single second. Back then, that was the absolute bleeding edge. Today, that number is, well, it's laughably small. The conversation's happening right now with the industry leaders, with the automotive trendsetters. They're not talking about 100 or 200 TOPS anymore, no way. They are demanding performance in the thousands of TOPS. This isn't just a little step up. This is a complete phase change. It's a whole new reality for the kind of horsepower you need to run the AI of today, let alone what's coming tomorrow.
So you're probably asking, how on earth did we get here so fast? Well, this incredible demand didn't just pop out of nowhere. It's the result of three distinct, compounding waves of AI innovation. First, we had the massive wave of generative AI, that initial explosion of networks that could create brand new content, text, images, code, you name it. That was shockwave number one. That then quickly morphed into agentic AI, where those super powerful generative models were put to work to create sophisticated AI agents. Think of chatbots that can actually understand context, reason through problems, and take action. And now, as we speak, we are right on the cusp of the next and maybe the most demanding wave of all, physical AI. We're seeing this huge surge in robotics really picking up steam in late 2024 and into 2025. And these things, from self-driving cars to warehouse spots, they need unbelievable processing power for real-time scene understanding, creating 3D models of the world, and planning complex actions on the fly. Each wave just piles on top of the last, pushing the compute needs up, not in a straight line, but exponentially.
Okay, so this relentless compounding demand for more and more compute has put the spotlight squarely on the workhorse of AI hardware, the Neural Processing Unit, or NPU. For years, the NPU has been the hero of AI acceleration, but as we're about to see, its very design, its fundamental nature, has a critical built-in flaw, an Achilles heel when it's faced with the insane pace of AI innovation.
Now, the NPU itself has come a really long way. Think about it. The original NPUs were basically giant specialized calculators. At their heart was a huge array of max, multiply accumulate units, that just do the basic math that is the bedrock of all neural networks. And the game back then was simple. It was a brute force race to cram as many max onto a chip as possible to get the biggest TOPS number. But that's not how it works anymore. Today's NPU is a much more complete, integrated subsystem. Sure, it still has that massive MAC array, but now it's surrounded by dedicated, hardened hardware blocks for all sorts of other specific tasks, things like the attention mechanisms in transformers, or common functions like ReLU and softmax, and normalization layers. This makes the NPU way more powerful for sure, but it also kind of doubles down on its fundamental weakness.
And this quote here from Amol Borkar at Cadence just nails the central conflict perfectly. On one side, you've got the AI software landscape, which is this constantly, relentlessly moving target, and on the other side, you've got the NPU, which is a hardened, fixed, unchangeable piece of silicon. They're operating on totally different timelines, and that creates a huge problem.
Let's really dig into this conflict. The AI world moves at the speed of research papers. A brand new network, a clever new math operator. It can pop up and become the new standard in just a few months. But hardware design? That's a slow, deliberate, incredibly complex process. An NPU is fixed function hardware. Once you finalize that design, the RTL, the architectural blueprint, and you send it to the fab, you are locked in.
That whole process, from design freeze to getting a physical chip back in your hands, takes 16 to 18 months. You are literally placing a bet today on the kind of AI models that haven't even been invented yet. So what happens when some genius invents a critical new function that your hardened silicon just can't handle? Well, your multi-million-dollar NPU is suddenly crippled. It becomes, as the source material puts it so perfectly, a very expensive dollar sink.
So what does this mean in the real world? Well, here's the dirty little secret of AI hardware. Despite what the marketing brochures might tell you, not all of an AI network actually runs on the NPU. It's just an industry-wide fact. Because of this moving target problem, some chunk of the workload always has to be offloaded to a more flexible, programmable processor. And we're not talking a trivial amount. Depending on the NPU's design, this offload could be as little as 5%, or it could be as high as a staggering 50% of the entire network. And this offload isn't a failure. It's just an inevitable strategic necessity because of that fundamental mismatch between software speed and hardware speed.
And this leads us to the absolute million-dollar question for every SoC architect out there. Okay, we've established that offloading isn't just a maybe, it's a fact of life. So when your super-fast hardened NPU hits a wall and finds a layer it wasn't built for, where do you send that work? What's the right target for this offloaded workload?
As it turns out, the traditional options all come with some pretty major compromises. It's a real Goldilocks problem. The most common target is the main CPU. But the CPU is already crazy busy. It's running the OS, managing apps, doing a million other things. Bogging it down with AI math creates a bottleneck for everything. Plus, architecturally, it's just the wrong tool for the job. Then there's the GPU. Now, a GPU is a parallel processing beast, but for these smaller offload tasks, it's like using a sledgehammer to crack a nut. Total overkill. And more importantly, GPUs are notoriously power hungry, which is a deal breaker in a phone or a car. So what about a standard digital signal processor, a DSP? Well, it's more power efficient, but a general-purpose DSP is bloated with features for things like audio or camera processing that are totally irrelevant to AI. So you're wasting precious chip area and power on stuff you'll never use. Every single path is a painful trade-off.
So, if the CPU is the wrong tool, the GPU is too big, and the DSP is too bloated, what's left? Well, this is where things get really interesting. Since none of the old answers work, a new, far more elegant solution has emerged, the purpose-built AI coprocessor. And this isn't just another block to throw on a chip, it's a whole new class of processor designed from the ground up to solve this one very specific, very critical offload problem.
So what exactly is an AI coprocessor, or AICP? Put simply, it's the NPU's perfect sidekick. The formal definition is that it's a specialized, programmable processor designed to complement an NPU by running the workloads the hardened NPU can't. And by doing that, it provides flexibility and, most importantly, it future-proofs the whole system. It really is the right tool for this very specific job. The key words to remember are specialized and programmable. It has everything it needs for AI, nothing it doesn't, but it stays flexible enough to adapt to whatever comes next.
Amol Borkar from Cadence has this fantastic way to think about it, which he calls the 3 Cos. First, it's a companion. In today's world, no AI subsystem is really complete without one. You're always going to have to offload something to get a network to run end-to-end. Second, it's complementary. It does all the things the powerful but rigid NPU can't. That means pre-processing data, post-processing results, or running specific layers like instance norms or softmax. And finally, it provides control. It can act like a little mini CPU for the whole AI subsystem, issuing commands and handling interrupts locally, without having to bother the main system CPU at all. Okay, that's the theory, and it sounds great. But talk is cheap, right? Let's see what this looks like in practice. We're going to move from the abstract concept to a concrete, real-world piece of hardware, the Tensilica NeuroEdge 130 from Cadence. This is the first licensable IP block of its kind, designed specifically for this co-processing job.
So what's the big headline number you need to remember? It's this: 30%. The NeuroEdge 130 is purpose-built for AI offload. It's based on Cadence's proven Vision DSP platform, but they've stripped out everything that isn't relevant to AI. And the result? You get all the performance you need for these offload tasks while using 30% less physical space or die area on the chip. For an SoC designer, that is a massive win. Less die area means lower manufacturing costs, and it means lower power consumption. In your phone, that's longer battery life. In your car, that's less heat you have to deal with. It's a huge advantage.
Now let's pop the hood and look at the specs. You can really see how it's tailored for this role.
It's built on a proven platform. It's scalable up to 512 max, and it supports all the essential AI data types like FP16 and bfloat16. But one of the most important things is that it's delivered as soft IP. Think of that like a recipe, not a finished cake. It means customers can implement it on any manufacturing process they want, from an older 28-nanometer node all the way to a bleeding-edge 2-nanometer process. And critically, for the car industry, it's ready for ISO 26262 functional safety, or FUSA certification. For automotive chips that have to last for years and years, that kind of future-proofing isn't just a nice-to-have, it's an absolute must.
Of course, brilliant hardware is only half the story. Hardware is only as good as the software that runs on it. The real magic here is how this thing integrates. For connectivity, it's got standard interfaces, but the crucial part is the software. It's fully supported by the NeuroWeave AI compiler toolchain. This thing is the brain of the operation. It can take models from PyTorch, Onyx, TensorFlow, and here's the key part. It automatically orchestrates everything. It analyzes the entire network and intelligently decides, ahead of time, which part should run on the powerful NPU and which part should be offloaded to the flexible AICP. All that complexity is just handled for you, which makes life so much easier for the developers.
Okay, this is my favorite part. This is where the story gets really compelling. The whole idea of an AI coprocessor isn't just some new concept from one company. It's an architectural pattern that has been independently discovered and validated by the biggest names in the business. They might not all call it an AICP, but they were all staring at the exact same problem, and they all came up with the exact same solution. It's a classic case of convergent evolution in hardware design.
All right, let's do a quick roll call of the industry giants. First up, NVIDIA. Take a look at their Jetson Orin and Xavier SoCs. The main AI engine is the DLA, the Deep Learning Accelerator. But what's sitting right next to it? The PVA, the Programmable Vision Accelerator. And its job? To handle all the pre- and post-processing and other stuff the DLA isn't optimized for. It's the AI coprocessor. Next, Intel's Gaudi 3 accelerator. The main number crunchers are the MMEs, the multiply matrix engines. But what's nestled right beside them? The TPC, or Tensor Processing Core. Different name, exact same function. It's a specialized DSP designed to handle all the custom operations that don't fit on the main engines. You see the pattern here?
The pattern continues with Qualcomm. Inside the Snapdragon platform, the main AI engine is the Hexagon Tensor Processor, the HTP. And sitting right alongside it, a highly capable vector unit that, quote, basically acts as an AI coprocessor. It's handling all the other math that doesn't map perfectly to the main tensor engine.
And finally, the big one, Google's TPU. At its heart is a massive tensor engine built for one thing, blazing fast matrix math. But that's not all that's in there. Sitting right next to that main engine are dedicated vector and scalar units. Their entire job is to handle all the other non-tensor stuff. This is the ultimate proof. All the major players, all working independently, all arrived at the same architectural conclusion. A powerful, fixed-function engine needs a flexible, programmable coprocessor to be complete.
So let's zoom out. What does all this mean? What this shows is that the rise of the AICP isn't just about adding one more component to a chip. It signals a much bigger, more fundamental shift in how we architect SoCs for artificial intelligence. It really is a whole new blueprint for the future.
Just think about the before and after. The old way, let's call it SOC 1.0, was to have these separate siloed islands on the chip, a CPU complex, a GPU complex, an NPU complex. Offloading a task meant shipping data all the way across the chip on a clogged main system bus. It was slow, power-hungry, and just painful. The new model, SOC 2.0, is so much more elegant. It creates a dedicated integrated AI subsystem. It's like a self-sufficient, high-tech neighborhood. Inside this block, the NPU and the AICP sit right next to each other on their own local high-speed fabric. Offloading becomes seamless, localized, incredibly fast, and way more power efficient. It's just a smarter way to build. And this brings us to our final thought for the day. As we move deeper into this era of physical AI, with robotics and autonomous systems becoming part of our world, the need for adaptable, reliable, long-lasting hardware is more critical than it has ever been. So this leaves us with a big question to think about. In a world changing this fast, is a purely fixed-function hardware approach even viable anymore? Or is this new model of an integrated, programmable, and future-proofed AI subsystem the only realistic path forward? Welcome back to the Dr. Pi channel. Don't forget to like and share.